very much. Okay, so today I will present the joint work with Bruce Hajek and Jiaming on SDP relaxations with both positive and negative results. So I think so the model we consider is slightly is more general than the graph theoretical models. So which is usually called the hidden community model. So what you observe is a matrix here, n by n symmetric matrix, and that's your data. And the community C star is a set of cardinality k. Here is chosen uniformly at random, and the community structure is manifested in the distribution of the entries of the matrix. If two indices belong to the same set C star, then they are distributed according to P, otherwise Q. Okay, so that's the thing. And the parameters, of course, varies the size of the matrix. And the goal here will be solely focused on exact recovery. So I want to have an algorithm which spits out C star based on observing the matrix that coincides with true C star with high probability. Right? So this problem, in fact, provides a very fruitful playground for studying the algorithmic aspects of statistical problems. In other words, there are situations where you can do it with maximum likelihood, but it's very expensive, and whether we can do it with efficient algorithms, right? This type of thinking. Okay, so special cases of this is when both distributions are Bernoulli, and that's usually called the PDS model, the planted dense subgraph, and clearly it generalizes the clique problem. So the matrix A will be the adjacency matrix of G and Q planted a GQP somewhere chosen at random, right? And there are many works on this model. And another one is when P and Q belong to the Gaussian family. In other words, what you're observing is the true matrix, which is a rank 1 matrix plus noise, right? So the ones correspond to the clusters will have an estimated mean, otherwise will be zero mean. And again, this is another problem which has received quite a lot of attentions due to its departure of its statistical and computational limits in various regimes. Okay, so for this talk, I will use a running example for the density subgraph problem. Okay, good. So this type of cartoon you have seen it for, I don't know, 5 times already. So in this case, you have n nodes, and you uniformly choose k nodes at random, which are these green ones, and they are densely connected, denser than the rest of the network, right? And you observe is something without the colors. In terms of adjacencies, you have a block structure like this, but what you observed are the ones without the indication of the memberships. Okay, good. So as a special case of this, when P is equal to 1 and Q is a constant like 1/2, and that's the famous planted clique problem, and there is the main problem in this type of model is to bridge the gap between computational methods and the information theoretical limits. So clearly, when the clique is size log n, you can do it by exhaustive search, and the best known algorithms, spectral algorithms, or even more sophisticated message passing algorithms only works when the size of the clique is root n, right? So, and it's in fact, people believe it's difficult and probably difficult in certain relaxation hierarchies. So what about is instead of the clique, you have a dense subgraphs? Well, first of all, the positive result is that if the community size grows linearly with network, in other words, like half of the network belongs to the same community, then the result is very positive in the sense that there's a threshold you can find, and which determines the possibility of finding the community. And not only that, you can achieve it with convex relaxations, the simplest natural relaxations, which is SDP in this case. Okay? But if the community size is sublinear, it turns out there are some barriers. So what happens is, for example, if the size of the community grows polynomially, and then there are some regimes where this is as difficult as planted clique. So the question is, well, in view of the fact that SDP start to work when it's linear, the question is, where is the true barrier let's say just for SDP relaxations, right? So where is that? The answer is is actually n over log n. So this is the point below which SDP start to lose its optimality guarantees, and that corresponds to somewhere very close to this point, right? So this is the main result, which I just said for the not only for the graph problem, but also for some matrix localization in a Gaussian model. If your size of the community is much bigger than n over log n, SDP is optimal, even with the sharp constant that coincides with the information theoretic limits with maximum likelihood. If it is on par with n over log n, then it's otherwise optimal, but there will be a loss of constant factor strictly compared to the information theoretic limits. And if you are little of n over log n, then you're going to be ordered away from the good, the optimal threshold. Okay, so this is the type of things. Okay, so what is the SDP relaxations? Well, in this case, what you have is you have a matrix, and you form its sufficient statistics, which is log likelihood ratio matrix. In the Gaussian or Bernoulli case, you can take this to be Aij itself, right? It's exponential family. And if you use a vector to indicate, the 0, 1 vector indicate the indicator of the true community, the maximum likelihood simply amounts to finding the densest K subgraphs. So you are choosing the matrix, submatrix, which has the largest sum of likelihood ratio, right? This is exactly maximum likelihood. Okay, so to obtain the convex relaxation for this, the usual way to do is to lift it by considering the rank 1 matrix that corresponds to the indicator, and rewrite the same optimization problem, and which in this case is still combinatorial because there is a rank 1 constraint, and the natural relaxation is to replace it by positive semi-definiteness, right? So that's the only difference between here. Now the question is, 2 minutes? Okay, all right. Okay, the question is, can you prove that it's nevertheless spits out the true solution that you want? And okay, so let me just skip the proof. Present the results. So essentially, you need both positive result and also impossibility result, right? So this was derived for a deterministic instance, and when you apply it, you just notice that all the min and the max and these operator norms will concentrate on certain values, and that's how you apply it to probabilistic models. So in particular, in this case, I just want to present to you the main thing in the proof. So to prove the positive result is very standard. You just need to, for this problem, you have strong duality. You just need to construct the needed certificate to certify the ground truth, right? And to prove the negative result, you can either prove the non-existence of these certificates, or you can construct something that beats the ground truth, right? So in this case, in fact, we implemented both methods. It turns out to give you the same result. And I just want to say one word about the primal proof, which is to perturb the ground truth so as to give you a better value of the objective value. So here you have the ground truth, which is 1 and 0 elsewhere. So what you do is you add 3 perturbations randomly to the ground truth. One is essentially depend on the matrix, the indices with the largest degree. Okay, 0. Okay, so sorry. So you can refer to the paper about the result. Just want to say one thing is that this result shows you that if the community size is smaller than n over log n, it's very difficult to solve. So maybe it translates into you have the block model with multiple community of the same size with size smaller than n over log n. In other words, you have more than logarithmically number of communities. The problem becomes difficult. And indeed, you can prove it's the same thing. So the usual relaxations start to lose its optimality once you cross a logarithmic number of communities, right? So the proof is similar, but it's not the same.